The human mind is capable of many extraordinary things. Science fiction even speculates what it might be capable of doing in the future. Currently, the human mind is the fastest computer on planet Earth. But will that always be true? I mean, will we ever build a computer that will outthink human beings? The thought of that is both terrifying and fascinating. Today, we're going to explore how to use math to answer the question, how fast do people learn? And we're going to do that using a differential equation on today's episode of Figure It Out. In order to explore how fast a person can learn, we will consider a situation that is task-oriented, such as learning a new job skill. The key to improvement is making small, smart changes, evaluating the results, discarding what doesn't work, and further refining what does work. Suppose we want to know how fast an employee learns a new task. One theory claims that the more a person already knows about a task, the slower that they learn. So let's translate that into a mathematical statement. If y% of a task has been mastered, then dy over dt is the rate at which the employee is learning. In other words, it's the rate at which the percentage is changing. In our situation, the claim is that dy dt decreases while y increases. That is, that the rate of learning decreases as the percentage of mastery increases. Consider some possible graphs showing the percentage of a task learned, y, as a function of time, t. If we look at these three examples, in the first graph, it shows an employee starting out at time equals 0 and eventually reaching 100% mastery. Whereas, if we take a look at the second graph, we notice that it is an employee that started a little bit later, time greater than 0, and eventually reaches mastery level of 100%. In the third graph, we see an employee who has started learning at time equals 0, but never actually achieved mastery. So in these three cases, we note that there's something common in particular all of them, and that is that a person's knowledge of a task cannot exceed 100%. And so this idea is captured in the horizontal asymptote at y equals 100. Setting up a differential equation to model how a person learns. In order to describe more precisely how fast a person learns, we need to know how dy dt, the rate, is related to y, the percentage of task mastery. So how does dy dt depend on y? Well, let's suppose that a person's rate of learning, dy dt, is equal to the percentage of the task that has not yet been learned. So we're going to set up a differential equation representing this idea. dy dt is the rate, and 100 minus y is the percentage of the task not yet learned. since 100 is the maximum and y is the percentage already learned. So whenever an equation involves a rate, like dy dt, we call it a differential equation. And our first attack here is to try to solve it numerically. So in order to solve many differential equations, we must often build the solution numerically step by step. What this equates to is starting with some known information or some initial condition and work our way out. So suppose that at time equals 0, the percentage of a task that someone knows is 0%. So our initial condition is y of 0 is equal to 0. Now, if we put this into our differential equation, we get 100 minus 0 is 100% per week. So in the initial stages, we can assume that 100% per week learning rate holds. So let's assume a 5-day work week. And in our 5-day work week, we know that our rate is subject to change. Okay, so our initial condition starts us off at 100%, and 1/5 of that would be 20% of the task learned. So in the first day, 20% of the task has been learned, and our rate has now been reduced down to 80% per week. All right, so after day 1 in our 5-day work week, we are now down to a learning rate of 80%. On day 2, let's say it's Tuesday, the person is learning at an 80% rate, and 1/5 of 80% is 16%. So by the end of the second day, the person knows a cumulative amount of 20% from the first day plus 16% from the second day. So a total of 36% of the task has been learned over the course of 2 days. Now, we want to continue this idea. Alright, and so if we continue in this fashion, we can compute the approximate values for our solution y, numerical solutions to our differential equation dy dt is equal to 100 minus y. So now, building a table of values, we can construct a graph to see what our solution looks like. In other words, get a gist for the overall trend. Approximate solutions work well when general solutions are typically hard to figure out. And so we see from our graph, although y is in fact increasing over time, the rate at which it does slows down as the percentage y increases. This is evident in the fact that the graph curves downward, and in calculus we say that the graph is concave down. Now what we would like is to find an explicit formula, in other words, to solve the differential equation explicitly. So if we can find a function y, a function of time, which satisfies our differential equation, we call it a solution to our differential equation. Now again, like I said before, finding a solution to a differential equation is often very difficult. So for our differential equation, what we can do is suggest a solution and see how that works out. So, for instance, our differential equation, dy by dt equals 100 minus y, has a solution of the form y equals 100 plus c times e raised to the negative t power. Now, it is easy to check that this is the case. If y is equal to 100 plus c times e to the negative t, differentiating that gives us negative c e to the negative t. And if we plug the y value into the right side of our original differential equation, we get the same thing. So it's easy to verify that this general solution works as a solution to our differential equation. And so if we input some specific data, like our initial condition of y of 0 equals 0, we can use this general solution to find what is called a particular solution. So in the event of just leaving it with an arbitrary constant c, we call that a general solution. When we use our initial conditions to find what the value of c is equal to, we call that a particular solution. So let's take a look at what that might look like, finding a particular solution with our particular initial condition. Our given initial condition again is when time is 0, the percentage learned is 0. So when we want to get our particular solution for our equation, we use the variable t equals 0, plug it into our general solution, and we find here that our c value is negative 100. Our arbitrary constant c is negative 100. So we get the particular solution y is equal to 100 multiplied by 1 minus e to the negative t. Given a general solution such as y equals 100 plus c to the negative t, one can sketch a family of solutions to our differential equation. Each time you give a different initial condition, you get a different constant c, and thus a different particular solution curve shown here. Slope fields and Eulers method. Consider a simplified version of our differential equation, dy dx is equal to y, using the variables x and y. We can check that y equals c e to the x is a general solution to our differential equation. Now this differential equation states that any solution y at any point xy is equal to the slope of the tangent line, or the derivative, at that point. For example, at the point 0, 1/2, the y value is 1/2. And that means that the derivative is equal to 1/2 at that point. The slope of the tangent line is equal to 1/2. Now, if at every point we sketch a mini tangent line to its corresponding slope given by the differential equation, we get something called a slope field. And a slope field is a way of visualizing the families of solutions. On the left here, you can see we've picked a certain set of initial conditions, and from that we can sketch out a solution which is in the slope field. So guess the form of the solution of this differential equation. Let's try an example. Alright, so here we see that dy dx is equal to negative x over y, and if we pick at every point in the plane, find the slope given by the equation negative x over y, we can draw the slope field. This slope field suggests that the general solution curve is a circle centered around the origin. And so we know that from geometry, x squared plus y squared equals r squared is the equation of a circle centered at the origin of radius r. So if we check to see if this is a solution to our differential equation, we need to use implicit differentiation to be able to find the derivative. Okay, so implicitly differentiating both sides, we get dy over dx isolated on one side of the equation, and on the other side it works out to be negative x over y. So we retrieve our differential equation through implicit differentiation. Eulers method and approximate solutions. So the 18th century polymath Leonhard Euler discovered a method for finding numerical solutions using a sort of bootstrapping method to build the solutions in small increments, starting with some small initial condition. The process is repeated until a desired accuracy is reached. So let's see how this works. Okay. Euler's method will start off with a particular starting initial condition, and we'll call that point P0. And from that, we'll then move on to a point P1. And from P1, we'll move on to a point P2, and so on and so forth. And as we do, we can sketch the graph accordingly. Alright, so to see how this process works, Euler's method, we need to start off by thinking about what sort of small increment step we might take. We call this in calculus delta x. If we move a small direction in the x direction, it's delta x. And here we're going to use a small increment size of 1/10 or 0.1. Alright, so considering our differential equation is dy dx equals y, starting at a particular point P0, we'll start at 0, 1, and we'll move an increment delta x of 1/10. That means we're going to move over in the x direction just 1/10 of the way. Now, in order to get to P1, we need to also know how much to move in the y direction, or delta y. So, to get delta y, what we do is we multiply the slope, given by the differential equation, at point 0, or P0 I should say, and multiply that by the increment delta x, and that's going to give us delta y, the amount that we have to add to our y value in order to move upwards. So here it works out to be 1 multiplied by 1/10, which is 1/10. So to the y value of 1, we add 1/10. So the y value of P1 is 1.1, or 1 1/10. So now we've moved from point P0, which is at 0, 1, to a point P1, which is at 1/10, comma 1 1/10. Alright, so it gives us here, if we build a table of values, continuing this process repeatedly, it helps us build the situation up numerically to whatever degree of accuracy we would like. Eulers' approximation solution method was used actually to help calculate trajectories by hand for NASA while attempting to put astronaut John Glenn into Earth's orbit during a time before the ubiquitous use of computers. Here, I introduce to you the method of separation of variables. So consider one of the differential equations from earlier, the one with the solutions that had circles around the origin. dy dx is equal to negative x over y, the slope field shown there on the left. So the solution curve we guessed by looking at the slope field to be x squared plus y squared equals some constant, which was just r squared. Okay, so the big question is, how does one obtain a general solution without having to guess based on the slope field? I mean, it's easy to check if we know what a solution looks like, but it's not so easy to find that solution explicitly. And this is one of the challenges of solving differential equations. Alright, so our approach in this particular case will be to use the separation of variables method, a method that only works for certain differential equations, certain ordinary differential equations. Okay, so we're going to start off by looking at our differential equation like it's a proportion, right? One fraction equal to another fraction. And we solve those proportions by cross-multiplying. So we get y times dy equals negative x dx. The variables have been separated on left and right-hand sides of the equation. And so by finding the solutions, what we mean is by integrating both of those sides to find the answer. And the antiderivative of y is y squared over 2, negative x is negative x squared over 2 plus a constant. And rearranging this equation, we get the equation x squared plus y squared equals c. One more simple example involving exponential growth and decay can be modeled with the differential equation dy dx is equal to k, some proportionality constant, times y. In other words, the rate of growth is proportional to the size of the function. When we separate the variables on the left and right hand side, we get the y's on the left and the x's on the right. So we can separate this differential equation. It is separable. So once we do that, we can then go ahead and integrate both sides to get the answer. Now, when we integrate dy over y, we get a natural log function, and we have to use its inverse, exponentiating, to find the solution y. And here we see the y is equal to an arbitrary constant c times e to the constant kx. And this is again why we get a lot of exponentials in the solutions to differential equations. An even more sinister differential equation, one with a substantial prize attached to it, is the Navierstokes equations, a set of differential equations involving partial differential equations that involve something called the del operator that looks like an upside-down triangle in the equation. The Clay Institute of Mathematics offers $1 million for a solution to this differential equation. Hey, thanks for watching. Please be sure to smash that like and subscribe button for more videos. Stay tuned.